Okay, in this lesson we're going to be looking at Unit 2, Chapter 1, Function Transformations. We're going to be looking at Reflections and Stretches, Part 1. And we're going to look specifically at how reflections and stretches affect the graph of y equals the f of x. We'll be focusing on developing an understanding of the effect of reflections on the graph of functions and their related equations, and developing an understanding of the effect of vertical and horizontal stretches on the graphs of functions and their related equations. First of all, let's start with reflections. A reflection in the x-axis will occur when y is replaced with negative y in the equation y equals the f of x. So y equals the f of x, I replace y with negative y. This would result in a reflection in the x-axis. Another way you may see that, of course, is y equals the negative f of x. You may see it written in this form as well. Both represent a reflection in the x-axis. A reflection in the y-axis will occur when x is replaced with negative x in the equation. So here y is replaced with negative y. Here x is replaced with negative x. This results in a reflection in the y-axis. Let's have a look at an example involving reflections. If we consider the graph of the function y equals the f of x right here, I want to reflect the graph in both the x and y axis. Let's just have a quick look at the definition here. A transformation where each point on the original graph has an image point resulting from the reflection in a line. We've done reflections previously in some earlier grades, so this shouldn't be an issue here. I want to simply take the graph and reflect it in both the x and y axis. Let's do that. Let's reflect it in the y-axis first. Use a different color here to represent the reflection. Obviously, if I reflect it in the y-axis, this point will not change. The point here will be reflected right here, okay? I have another point as a result of reflection right here. I have another point right here, and another point right here. We want to make sure that we join them up in the exact same way that they're joined up in the original graph. So let's do that. And here is what the new graph reflected in the y-axis will look like. So there's an example of a reflection in the y-axis. Let's have a look at the coordinates of some of these points, and let's see what's actually happened to them. Here, for example, the point 4, 0 has been reflected to negative 4, 0. Here I have a point 1 and 2 that's been reflected to negative 1 and 2. If you look closely, you can see that the y-coordinate hasn't changed, but the x-coordinate has become the negative value of the original. So here we got 4 has become negative 4. Here 1 has become negative 1. Sorry, negative 1 has become positive 1, but the y-coordinate hasn't changed. So you can see that the mapping rule here for this is simply going to be xy maps to negative x, comma, y. This will be the mapping rule for reflection in the x-axis. Sorry, that's a reflection in the y-axis. My apology. That should have been down right here. Let's move that down. My apologies. It should have been down here. I did my reflection in the y-axis first. There we go. That's better. Reflection in the y-axis. I got a x becomes negative x. Y coordinates do not change. Reflection in the y-axis. The equation of the translated function with a reflection in the y-axis. So negative in front of the x there. So we end up with the equation looking like this. Y equals the f of negative x. Reflection in the y-axis. Okay, let's quickly do a reflection now in the x-axis. I'll use a different color here for this one. Take the original graph and reflect it in the x-axis. This point doesn't change. We have the coordinates of a point here. Let's see, 1, 2, 3, right there. We have another point here. We have another point there. And finally, we have a point right here. Let's join them up and see what the graph looks like. And there's the graph reflected now in the x-axis. Let's have a look at the coordinates of some of the points here. This is the point 3 and 3. The coordinates of my new point after reflection of the x-axis is 3 and negative 3. Note that the y-coordinate has now changed. Let's look at another example here. The point -1, 2 has become -1, -2. Note again that the y-coordinate is now changing in both examples that I chose. So my mapping rule becomes xy maps to x, comma, -y. There's the mapping rule for a reflection in the x-axis. And the equation can be written in two forms. I can write it like this: -y equals the f of x, or I could write it as y equals the negative f of x. Note the location of the negative. The negative in front of the f of x means a reflection in the x-axis, right here. A negative inside the brackets means a reflection in the y-axis. Let's move on. Let's now have a quick look at stretches here. A vertical stretch will occur when y is replaced with 1 over ay in the equation. So here's the equation, y equals the f of x. I replace y with 1 over ay. This will result in a vertical stretch of a. A horizontal stretch will occur when x is replaced with 1 over bx in the equation, y equals the f of x. So notice here, y is replaced with 1 over ay, x is replaced with 1 over bx. Vertical stretch of a in this case, vertical stretch of b in this case. Now again, you need to realize that this equation may also be written like this: y equals a times the f of x. Same equation. Think about multiplying both sides by a. This is what you will end up with, of course. A vertical stretch of a horizontal stretch of b. Let's look at an example of each of these. We're given the graph of y equals the f of x. Here it is. We're asked to transform the graph of f of x to sketch the graph of g of x. In this case, the g of x is 2 times the f of x. We're asked to describe the transformations that are occurring, state any invariant points, state the domain and range of the functions. Let's do that. First of all, let's transform the graph by using our table of values down here. The original graph has x at -6, y is at 4. X is -2, y is 0. Look at the original graph. X is 0, y is 2, x is 2, y is 0, x is 6, y is 4. The new function, g of x, is 2 times the f of x. 2 times the f of x simply means double our f of x values. So therefore, 4 times 2 is 8, 0 times 2, 2 times 2, 0 times 2, 4 times 2. Now let's plot our new points for the g of x. So I got -6 and 8 is a point. I've got -2 and 0. I've got 0 and 4. I've got 2 and 0. And I've got 6 and 8. Let's draw up these points, see what the new graph looks like here. There it is. You can see that this graph has been stretched vertically by a factor of 2 units. So it has to describe the transformation. It's a vertical stretch of 2. Some students, again, may want to see this written as 1/2 g of x equals the f of x. Same thing, of course. It's a vertical stretch of 2 units, and that's the result of the graph right there. It says state any invariant points. There are 2 invariant points. The invariant points are where the graphs have the exact same values. So we have 2 invariant points at -2 and 0 and at 2 and 0. These are our invariant points right here and here. These 2 points are the same on both graphs. State the domain and range of the functions. Let's do that. The original function has a domain between -6 and 6. Again, you think about the values of x that I can find points on the graph. I can find points on the graph between -6 and 6. The domain of the new graph hasn't changed. The domain of the new graph is still between -6 and 6. Oops, let's move that x over here. So x is still between -6 and 6. The range of the original graph was between 0 and 4. Again, I can find points on the graph between 0 and 4. Let me delete that. Now let's look at the range of the new graph. The new graph has points between 0 and 8. So the range has changed now. Y says that y is between 0 and 8, where y is nominal var. Let's state the mapping rule, because it's important to be able to get the mapping rule for all of these. The mapping rule is simply going to be, because it has a vertical stretch of 2, we have x, comma, 2, y. That's a vertical stretch of 2 units. Okay, so there's an example of a vertical stretch. Let's do an example of a horizontal stretch. Notice here now, x is replaced with 1 over 2x. This represents a horizontal stretch of 2 units. So to describe the transformation, it's exactly that. It's a horizontal stretch of 2. So we're going to stretch this graph horizontally by a factor of 2. We're going to do it this time using the mapping rule. XY maps 2. A horizontal stretch of 2 would be 2x comma y. Let's take the points that you see on the original function, let's plug them into our mapping rule and create a new set of points. We have a point -4 and 4. Plug that in, we get a point -8 and 4, because 2 times a -4 is a -8. So I got a point at -8 and 4. -8 and 4. 1, 2, 3, 4, 5, 6. Got quite enough room here, so let's call this here -8. It's fine. -8 and 4. If we extend our line, of course. And the same thing on the other side. I think I need to extend it to get to +8, because I think that's going to be a point as well. Might as well do that point now, I guess. We had a point at 4 and 4. So we end up getting a point at 8 and 4. This will be translated to 8 and 4, which again is right there. We have a point at -2 and 0. Plug that into your mapping rule, and you'll get -4 and 0. We have a point at 2 and 0. Plug that into your mapping rule, we get a point at 4 and 0. And finally, we have a point at 0, 2. Plug that into your mapping rule, and we end up with 0, 2. So that point hasn't changed. Let's join them up, see what the graph looks like here. Here's my graph stretched horizontally now by a factor of 2. And if you look at the graph, you can see that's exactly what's happened. The graph has been stretched horizontally, in this case by a factor of 2. Invariant points, there's only one invariant point this time. It's the point 0, and 2 is the invariant point. The domain and range of the function, let's have a look at them. The original function, in this case, the domain is between -4 and 4. And the range of the original function is between 0 and 4. Let's look at the domain and range of the translated function. The domain of the translated function is between -8 and 8. It's doubled horizontally, as you can see. And the range hasn't changed. The range is still between 0 and 4. And there is an example of a horizontal stretch of 2. Let's look at some examples involving horizontal and vertical stretch. What are the coordinates of the image point A prime if the point A on the function f of x is mapped onto the transformed function g of x, which you see here. All we need to do is create a mapping rule, plug the point in. To create the mapping rule here, some students can do it directly from this equation. We have a vertical stretch here of 1/3. We have a horizontal stretch of 2. That's our mapping rule. Some other students may want to get this equation written in what we call transformational form, whereby we multiply both sides by 3, and we get 3 times the g of x equals the f of 1/2 x. And again, some students like to see it in this form. You take a reciprocal of the 3 to get 1/3. You take a reciprocal of the 1/2 to get 2. Regardless of which form you're used to looking at, doesn't really matter. There's our mapping rule. We simply need to plug in our point -4 and 6 into that mapping rule and see where the coordinates of the new point will be located. So 2 times a -4 is a -8. 6 times a 1/3 is 2. -8, 2. The correct answer is A. Example 5. What are the coordinates of the invariant points when this function is reflected in the y-axis? Now, the first thing we need to be able to do is do a sketch of this function. This is an absolute value graph. It's an absolute value graph with its vertex at 2, 0. You think about the original function, y was the absolute value of x. It's been moved 2 units to the right. So if I do a sketch of this graph, this is what it's going to look like. It's going to look something like this, whereby the vertex of this V-shaped graph is located at 2, 0. Now, the slopes of each of these lines are 1 and -1. So this one's got a slope of 1. This one's got a slope of -1. And the y-intercept, if you want to find the y-intercept, of course, the y-intercept occurs when x is equal to 0. If you plug in x equals 0, I get the absolute value of -2, which is 2. The y-intercept of this graph is 2. If I take this graph now and reflect it in the y-axis, you should agree that the vertex is going to be located at -2, 0, and a reflection of the y-axis will result in a graph that looks like this. There's a reflected graph in the y-axis. The question is, what are the coordinates of the invariant points? There's only one invariant point, and is located at 0 and 2. Correct answer is C. So we'll look at another example here. The graph of the function y equals the f of x is shown. What is an invariant point under this transformation right here? Notice now that we actually have 2 transformations occurring. We have both a reflection occurring and we have a vertical stretch. You can see that this results in a reflection in the x-axis, and we also have a vertical stretch of 2. Some students may want to write that like this to be able to identify the reflection of the x-axis and the vertical stretch of 2. Regardless how you write it, let's create a mapping rule here. Mapping rule is going to be xy maps to x, comma, -2y. What I would do is I would take all the points on the original graph now, plug them into that mapping rule, and find the graph of the translated graph. Let's sketch the translated graph based on these points. Okay, let's plug them in. We got a point at -5, 2. Plug that point in. -5, 2, this one right here, okay, this point right here, will become -5 and -4. -5 and -4 is a point on my graph. There we go. That's been translated there. Let's plug in the point -3, -2. That will give us -3 and 4. -3 and 4 is a point on my graph. Let's take this point right here, located at 1 and 2. Plug that into my mapping rule. I'll get 1 and -4. And finally, let's take the point 4 and 2, plug into your mapping rule. You'll get 4 and negative 4. Let's join these points up and see what our graph looks like. There is my translated graph. Now, if you look at the translated graph, you will see again that there are two invariant points. Again, invariant points are points that are the same on both graphs. The two invariant points occur here and here. One is at negative 4, 0. The other is at negative 1, 0. So the answer is negative 1, 0. It didn't ask what are the invariant points. In other words, list both. It only asked which is an invariant point. There are two. We only wanted one. Negative 1, 0 is the one that we're looking for. Last example, I think. The graph of y equals the f of x is transformed to y equals the f of negative x. If y equals the f of x passes through the point 3, 5, which is true for the image y equals the f of negative x? Well, y equals the f of negative x, we should recognize immediately that's a reflection in the y-axis. Reflection in the y-axis, so we know the answer is either C or D now. And all we need to do is create a mapping rule for our new function. xy maps to reflection in the y-axis, so negative x, comma y. Negative x, comma y. So the point 3, 5 will be mapped to negative 3, 5. Correct answer is D. Correct answer is D. Okay, I think that's the last example. Here's a list of the key ideas again for the lesson. We talked about a number of things here. We talked about the fact that if you see an equation written like this, y equals a negative f of x, or negative y equals the f of x. That's another way of seeing it, right? It represents a reflection of the y-axis, and the mapping rule is going to be x comma negative y. And an example of a reflected graph will be one like you see here. Here's the original graph. We're reflected in the x-axis. So a negative in front of the y here results in a reflection of the x-axis. If I got a negative here in front of the x, like I see here, it results in a reflection of the y-axis. And my mapping rule looks like this. xy maps to negative x comma y. And again, it's a reflection of the y-axis. We also looked at stretches. We looked at y equals the a times the f of x, or another way of writing that you may see it, is 1 over a. Y equals the f of x, same thing. This results in a vertical stretch of a. We know if a is less than 0, then the graph is also reflected in the x-axis. The mapping rule is simply xy maps to x comma ay. Of course, here with the b in front of the x represents a horizontal stretch of 1 over b. If b is less than 0, the graph is also reflected in the y-axis, as we said right here. Mapping rule, xy maps to x over b comma y. And again, here's an example of a graph that's been stretched horizontally by a factor of b. And that ends this lesson.